Hi all, welcome to another lecture series of electrical machine design, and today we are going to discuss the output equation of AC machines. So the output equation of AC machines means we have to derive the output equation for that is suitable for induction machines and also for synchronous machines. Okay, so we are starting by considering an M-phase machine. Okay, consider an M-phase machine having one circuit, that is one parallel path per phase. Okay, and the kVA rating of the machine Q is equal to, we know normally we will be writing the Q as Q is equal to V phase into I phase into 10 raised to minus 3. Okay, this is actually the kVA rating, that is output. Okay, and here this Q is equal to number of phase, additional time number of phase is the then output voltage per phase and current per phase into 10 raised to minus 3. So if you are considering a 3-phase machine, the Q will be equal to 3 into V phase into I phase into 10 raised to minus 3. Okay, and if you are considering an M phase machine, it will be equal to M into V phase into I phase into 10 raised to minus 3. So like that. Okay, so here the terminal voltage of each phase may be taken equal to the induced EMF per phase. Therefore, instead of this V phase, we are writing E phase, E suffix phase here. Okay, and we know the equation for E phase, that is induced EMF per phase. E phase equal to 4.44 F5 T phase into kW. That is for rotating machine. So this F is equal to frequency, then phi is the flux per pole, and T phase is the turns per phase. Okay, turns per phase, and kW is the winding factor. So just we are substituting this equation, that is the equation for E phase, in the equation of Q. So Q becomes M into, instead of E phase, just substitute these values, that is 4.44. You can see here 4.44 F5 T phase into kW into I phase into 10 raised to minus 3. Okay, and in that we are going to substitute the value of F as PNS by 2. That we know, that is, we know that the synchronous speed in RPM, NS equal to 120 F by P. Okay, that we know, and also we know that this NS is in rotation per minute, RPM. Okay, and this here it is a small ns. Okay, so the small ns means rotation per second. Okay, rotation per second. So always this small ns will be equal to capital ns by 60. Okay, capital ns by 60. So instead of this capital ns in the equation, that is ns equal to 120 F by P, instead of this ns, substitute the value of ns into 60. So from that we obtain the equation F is equal to P into ns by 2. I hope it's clear, and therefore we can write the output equation Q as M into 4.44. Instead of this F, we are substituting PNS by 2. Okay, PNS by 2 into phi into T phase into kW into I phase into 10 raised to minus 3, and just we are rearranging, that is this 4.44 and 2 can be cancelled, and it becomes 2.22. Okay, 2.22, and this 2.22 can be written as 1.11 into 2. Okay, 1.11 into 2, that you can see here, 1.11. Okay, and 2 here. Okay, 1.11 into 2, and we have just write together the values P and phi. Okay, and 2m into I phase into T phase. Just we have rearranged this equation, that's all. Okay, and we know that the current, okay, current in each conductor, that is IZ, current flowing through each conductor, IZ is equal to I phase. Okay, because here we already said that there is only a single circuit, that is only a single parallel path. Okay, which means IZ equal to I phase. Okay, and the total number of armature conductors Z is equal to, how can you find the total number of armature conductors Z? That is, we know T phase, we know the value of, sometimes we maybe know the value of T phase, that is turns per phase. Okay, so if you are multiplying this T phase into 2, it becomes conductors per phase. Okay, 2 into turns per phase means conductors per phase. Okay, and if you are having m number of phases, okay, so the total number of conductors will be m into 2 into T phase. Okay, 2m into T phase. So here for getting the total electric loading, that is IZ into Z, you have to multiply this term with IZ. Okay, so it becomes 2m into I phase into T phase, and here in the question you can see a term 2m into I phase into T phase. So instead of this 2m into I phase into T phase, you can substitute the value IZ into Z. Okay, so the value output equation Q becomes 1.11 into KW into P phase into IZ into Z into NS into 10 raised to minus 3, where we know that this P phase is the total magnetic loading and IZ into Z is the total electric loading, and small ns is the synchronous speed in RPS, rotation per second. Okay, and we have to derive the output equation Q in terms of our specific magnetic loading and specific electric loading. Okay, so in the equation itself we have to substitute the value of BAV and AC, that is specific magnetic and specific electric loading, and BAV we know that it is equal to the equation will be equal to P5 by pi dl. Okay, so instead of this P5 here, you can substitute BAV into pi dl, BAV into pi dl. Okay, and also this IZ into Z. Okay, that is we know that the specific electric loading is equal to IZ into Z by pi d. So instead of this IZ into Z, just substitute AC into pi d. Okay, so you can see here P5 is equal to pi d into BAV and IZ into Z is equal to pi d into AC. Okay, so the output equation Q becomes 1.11 into KW into, instead of this P5 just substitute pi d into BAV, and instead of this IZ into Z just substitute pi d into AC. Okay, and by rearranging and multiplying with this value 1.11 with the pi square. Okay, pi square means that is 3.14 whole square, and the equation Q becomes 11 BAV AC KW into 10 raised to minus 3 into d square lns. Okay, and we can substitute the value C0 here. Okay, substitute the value C0, that is this is a constant, this 11 BAV AC KW into 10 raised to minus 3 will be a constant. Okay, so we are denoting that constant as C0. Okay, and output equation Q becomes C0 d square L into ns. Okay, so here the value of D and L will be varying. Okay, that actually we have to design the value of D and L. So from this output equation Q is equal to C0 d square ns, we have to find the value of main dimensions of the machine, that is capital D, that is diameter, and the length of the core L. Okay, so this is the same equation for the induction motor also. I hope it's clear. And this is the output equation of an AC machine, and the C0 is called the output coefficient. So thank you.